Okay, so hopefully you are with me on understanding both how we got to minus 70, which is resting membrane potential, and then that depolarization is moving closer towards zero, meaning that you're less polarized. Closer, the inside and the outside, the extracellular fluid and the intracellular fluid are more similar to one another. That's depolarization. Hyperpolarization is when the inside and the outside become more electrically different. That would be moving from minus 70, which is that resting membrane potential, to maybe minus 80, minus 90. Okay, because now what we're going to do is we're going to start talking about the concept of graded or local membrane potentials. So resting membrane potentials occur in every single cell. Every single cell is close to minus 70, not exactly at minus 70. And the outside of the cell membrane is slightly positive and the inside of the cell membrane is slightly negative. And if you measured the difference, it would be about minus 70. But a graded or local membrane potential is going to change that. It's going to start from minus 70 and change it. Okay, so first let's sort of assess the name. Why is it called graded or local? Okay, so it is, let's start with a neuron. Okay, so you guys learned neurons and anatomy, and let's just look at a little bit of the anatomical terminology. First of all, this is the neuron cell body, or the soma. These represent dendrites, right? This is the axon, and the axon hillock is the first part of it. Okay, so what will be important to us in the next part is that what happens at the cell body has to affect the axon hillock for us to go from a graded potential to an action potential. So a graded or a local potential is a local flow of current that decreases in intensity with the distance traveled. So that's what this figure is trying to show, meaning that, for instance, doesn't have to be sodium, but if I opened a gated sodium channel right here, it would cause a change in membrane potential, yes? And the change in membrane potential, hopefully you'll understand if I say that if I open a gated sodium channel, then sodium will go from the extracellular fluid to the intracellular fluid. And since I'm taking positives, sodiums, from the outside to the inside, that will be a depolarizing change, so it would look like this, okay? So if I measured the difference right here at the site that I opened the gated sodium channel, it might look like this, going from minus 70 to, I don't know, let's say minus 60. But if I measured it over here, because it decreases in intensity, if I measured it over here, it wouldn't be as massive a change. So it's a local flow of current that decreases in intensity with the distance traveled. It will go a short distance and then it will die out. It's decremental. So meaning that kind of like throwing a pebble in a pond or a boulder in a pond. If you throw a pebble in a pond, it's not going to be a massive change either at the site, but certainly not over on the other side of the pond. But if I throw a boulder in a pond, it will be massive here, and then the waves that I feel will be less over on the other side of the pond. Okay, so it's called local or graded because it's decremental. As you move further away, the intensity changes. It's also called graded because it can be strong or weak. So if I opened one gated sodium channel over here, I might get this. But what about if I opened 5 gated sodium channels over there? I might get this kind of change. So it can be strong or weak. Okay, so local because wherever you drop the pebble in the pond, you're going to have the most impact. and graded because there are strong ones or weak ones, because the magnitude of the current varies with the intensity of the stimulus that set it off. The other thing is that graded potentials can also be depolarizing or hyperpolarizing. Okay, so one of these, Y or Z, is recording what happens in a membrane if you open a sodium channel, and the other one is recording what happens in a membrane if you open a potassium channel. So let's talk about that. All right, and talk about how you would know, because hopefully you get this, but I don't know if you do. Okay, this guy right here. Okay, Z. Let's talk about what is happening there. So I'm starting at minus 70, and they didn't put it here, but let's start at minus 70 because that's where it is on average. So what would be depolarizing? If I opened a gated sodium channel and sodium moved from the extracellular fluid to the intracellular fluid down its electrochemical gradient, would that depolarize the cell or hyperpolarize the cell? So this is opening a gated sodium channel. Okay, that's depolarizing. But what about this one? How do you cause that to occur? Is that opening a gated sodium channel or opening a gated potassium channel? So potassium is positive, so it's not the charge of the ion, it's the direction that the ion will go. If I open a gated potassium channel, potassium will move down its electrochemical gradient from the intracellular fluid to the extracellular fluid. So it will take positives from the negative inside and put them into the positive outside, making the inside and the outside more different or hyperpolarized. Okay, so this one represents opening a gated potassium channel. Okay, so graded potentials can be depolarizing or hyperpolarizing. So let's see if you guys can practice with the terminology just a little bit. So on this diagram that's in your notes, you're going to sketch the membrane potential. So the important thing is to put the terminology together with the idea. Okay, you're going to sketch the membrane potential recorded in a cell as it begins with resting membrane potential and undergoes a hyperpolarizing graded potential. So I'm going to do this with you, and I'm going to ask you some questions, and I want you to do it in your notes at the same time. You can pause as many times as you want. Okay, so here we go. We are going to sketch the membrane potential recorded in a cell as it begins at resting membrane potential. So which of these is resting membrane potential? So minus 70 is resting membrane potential, but I'm going to have some questions for you about that. Begins at resting membrane potential and undergoes a hyperpolarizing graded potential. So I'm going to start out, I don't know how long I went, but which direction am I going to go for a hyperpolarizing graded potential? I'm hyperpolarizing, so I'm going to get more polarized further from zero. So a hyperpolarizing graded potential. So that's hyperpolarizing right here. So I have some questions for you. So let me change colors for just a second. So I'm going to ask the same questions on the diagrams that we do every single time. So first question is, what type of channel got me to minus 70? What kind of channel got me there? So how did I get to minus 70? Was it a gated channel? Was it a leak channel? What was it? So remember that minus 70 was because of leak channels. And remember that in order to get to minus 70 initially, the potassium leaked faster because there was a greater concentration gradient and because there were more potassium channels. So leak channels importantly got me to minus 70. And next question is, what kind of channel is here? What is doing that? So, is it sodium or potassium? And is it opening or closing? And is it gated or leak? So what kind of channels are going to be here? So it is hyperpolarizing, and graded potential. So what is it going to be? It's going to be opening, because they're going to move, right? And it's going to be a gated potassium channel. And why is it potassium? Because if I open a potassium channel, the potassium is going to go from the inside to the outside down its electrochemical gradient. Okay? All right, so now let's do the next one. The next one is kind of exactly what you would expect if you were thinking. So on the diagram below, sketch the membrane potential recorded in a cell as it begins at resting membrane potential and undergoes a depolarizing graded potential. Now, again, it's really important that you understand that, like, this terminology right here is putting the terms together with the functions. And it's super important that you understand the words that I will use to ask complex questions. So I'm trying to make sure that you can do this when you are actually practicing in your notes. So we're going to do it again. We're going to practice this kind of same thing. And we're going to do this one. All right, here we go. Same business, different color. Okay, so sketch the membrane potential recorded in a cell as it begins with the resting membrane potential and undergoes a depolarizing graded potential. So same blasted question. I begin at resting membrane potential. What is that? That's minus 70, right? Okay. And I'm going to undergo a depolarizing, closer towards zero, graded potential. I don't care about the magnitude because I didn't tell you. Okay? Depolarizing graded potential. I'm going to ask you the same questions that I asked you before. And that is, how did I get to minus 70? What kinds of channels were involved in getting to minus 70? Minus 70 was because of what kind of channels? Was it gated channels? No, gated channels change from resting membrane potential. How did I get to resting membrane potential? Resting membrane potential is because of leak channels. Leak channels that allow unequal leaking of sodium and potassium. Okay, next question. What's going on here? What kind of channels, sodium or potassium, gated or leak, and open or closed? So how did I get there? Okay, so with this one right here, because I'm depolarizing, it's telling me that I'm sodium channels because, again, sodium will move from the extracellular fluid to the intracellular fluid, right? When given the opportunity. And so those, and are they gated or leak? Well, leak does resting membrane potential. Gated changes resting membrane potential. And are they open or closed? They're open. So this is opening gated sodium channels. Okay, so now leading into the next topic, which is really difficult for me to teach on distance learning, but I'm going to do my damnedest. So if the stimulus that is initiating the graded potential is a chemical, and it's a whole bunch of chemical, let's say a neurotransmitter like acetylcholine, and it binds to and opens a chemical or ligand-gated sodium channel, will it cause depolarization or hyperpolarization? So if I have a ligand-gated sodium channel and there's sodium, the ligand-gated sodium channel binds to and opens the sodium channel, will it cause depolarization or hyperpolarization? So this is important. So what do you guys think? So if the stimulus initiating the graded potential, whatever stimulus it was, whatever opened the gated channel, binds to and opens a ligand-gated sodium channel, will it cause depolarization or hyperpolarization? So it will cause, because it's sodium, right? It will cause hyperpolarization. Right? Okay. So the stimulus doesn't have to be a chemical, but chemical gated channels are easier for us to picture. So I'm going to give you an animation to watch that shows you this. All right. Oops, where'd you go? Come back. There we go. Ooh, frozen. Why are you frozen? Give me a second. Stuff happens, man.
Action potentials arriving at the presynaptic terminal cause voltage-gated calcium ion channels to open. Calcium ions diffuse into the cell and cause synaptic vesicles to release acetylcholine, a neurotransmitter molecule.
Okay, ignore the first part.
Acetylcholine molecules diffuse from the presynaptic terminal across the synaptic cleft and bind to their receptor sites on the ligand-gated sodium ion channels. This causes the ligand-gated sodium ion channels to open, and sodium ions diffuse into the cell, making the membrane potential more positive.
Okay, so exactly what we saw there would be represented as a depolarization closer towards zero.
If the membrane potential reaches threshold level, an action potential will be produced.
Okay, so just to give you a visual of ligand-gated sodium channels causing depolarization. So sodium moves into the cell down its electrochemical gradient. The membrane begins to depolarize as the intracellular fluid becomes less negative with reference to the ECF. Now, this can lead to the next thing, which is the hard part to teach. So if this were in a neuron, so go here. If this were in a neuron, if the initial stimulus was intense enough, like lots of chemical binding to lots of ligand-gated sodium channels over here, then lots of sodium moves in. It causes a big depolarization. So what do I mean by a big depolarization? Like if over here at this side, it recorded a huge depolarization, then over here at this side, it would be that big, right? Not drawn to scale. Causes a huge depolarization. As sodium floods in, the flow of current from the graded potential could be big enough to cause a big change in the axon hillock. And the axon hillock over here is the really important part. So the axon hillock is a really important part because it's the first area that you're going to learn that has voltage-gated sodium channels. Okay, so if the axon hillock gets the voltage-gated sodium channels open, you will get a new type of membrane potential. The magic voltage for the axon hillock is called threshold, and it's about minus 55. It averages about minus 55. So if you hit threshold or stimulus, you get a new kind of channel involved. So thus far we have involved leak channels and we have involved gated channels, but let's call them ligand gated channels to separate them from what we're going to do next, which will be the voltage gated channels. Okay, so if you open the next one, you will get a new kind of stimulus. You'll get a new kind of potential. And that magical thing that opens the new kind of channel is called threshold. So I'll stop there and then we'll do action.